So, hello everyone, and welcome to the University of Manitoba's Resources for Agriculture Engineering. I am your host, Udwak Edet, an agricultural research extension engineer in the Department of Biosystem Engineering. Our mission is to forge meaningful connection with agricultural community and help farmers address their engineering needs and aspiration through dissemination of research work, innovation, and practical solutions in agriculture. Today, we have in our midst Dr. Ranjan Sri Ranjan. He's the professor in the Department of Biosystem Engineering at the University of Manitoba, um, teaching and doing research in water management for the past 35 years. He's currently supervising three PhD students and three MSc students and has supervised over 75 graduate and undergraduate students. Dr. Ranjan has been conducting irrigation and drainage research in fully instrumented field in Manitoba and helping farmers see the benefits of advanced water management technique through computer modeling and simulation using long-term weather data. He is pioneer in teaching controlled drainage with sub-irrigation in his research plots in Manitoba, showing the economic and environmental benefits. He holds many competitive grants, including NSEC, and has published over 120 papers at both national and international journals and conference proceedings. He has also um, been a part of 30 invited presentations in Canada, in US, India, China, Bangladesh, and Sri Lanka. He has 4 patents on electronic instruments that were designed to improve water management at the field level. So today we hear Dr. Ranjan tell us more about controlled drainage and how that can actually help farmers and installers. Dr. Ranjan, over to you.
Thank you, Duak, for the kind introduction. Please stop me as I speak and ask questions if you need to. It's kind of a discussion about the work we have been doing since 2009, especially in Manitoba. So without further delay, I will just go on to the topics I want to discuss today. But before I begin, I want to acknowledge all the people who made this research possible, especially my former students and current students, Imaka Indule and Afomante, M. Cordero, Sachidanandam, and those are former students, and then Mr. Kudahe, Ms. Ahilation, and Ms. Karagalan, and Ms. Kaur, and Ms. Kaja, Mr. Kaja, they all helped somewhere in different parts of these projects. This wouldn't have been possible if I didn't have the sites at Hespler Farms originally. Then I moved on to a site in Pesay, where Dr. Nimral Hari and his staff has been very helpful in implementing. And obviously, without the support of Manitoba agriculture personnel like Juan and Brian and other staff, Mitchell Timmerman and others, it has been wonderful opportunity to collaborate and do things. Of course, funding is from Natural Science and Engineering Research Council, ESCAP program, MyTax, and Manitoba Agriculture as well. And the students have been supported through University of Manitoba Graduate Fellowship. So I want to acknowledge that before I even begin, because none of this will be possible without all this support. So just to go on to what we're going to talk about today, I'll briefly mention benefits of drainage for those who are not familiar with the concept, how drainage control structures work, which is kind of new in the last, I would say, decade and a half, and something that we have been trying to test in Manitoba, that is irrigation supplied through the tiles. And in order to optimize this system, we have been actually trying to model the system for the different fields using different models like drain mod and as well as hydrous modeling, so we can optimize the design. Some of the benefits of drainage: obviously water needs 5 times more heat to warm up compared to dry soil. And the only source of energy to warm up the soil is the sun's energy. Therefore, a drained field will warm up much faster, allowing cultivation and operation much earlier. Even if they are planted, soil will be ready for germination much earlier than drained soil will be better than undrained fields. In addition, wet soils also have the high risk of soil compaction. You want the soil to be lower than the lower plastic limit, at least in the top 2 feet of the soil, so we can get on the field without damaging the soil. So drainage certainly improves the number of trafficable days, extending the time available for using your machinery. So basically, it's a win-win in that sense. We use, as I said earlier, drain mod and the hydrous as for modeling, so we can optimize the design. And I will show you examples of that as we go along. Now, here is a complex graph showing the water table depth from the ground surface. So I'm going to show you, in this case, this is a soil surface, and the tile drain is installed at, in this case, 0.9 meters below. And we have in the middle of the field a water level sensor in a piezometer that monitors every 3 hours what the water level is. So if you look at this carefully, the blue line here represents the drained field, and the red line represents the undrained field. And you can see within 3 days of the rainfall, the water table went up near the surface and it dropped. In both of them, when you compare, the drop in the no drain field was only 0.44 meters in 3 days, whereas in the drained field, it was 0.7 meters in 3 days. So the faster you can bring the water table down, the better it is for the crop. Obviously, the drain spacing will affect that. The closer the drain spacing, the faster the drop. But the closer the drain spacing, it also costs more to install at the installation. So we will actually talk about the spacing of the tile later on as I proceed in the next few slides. So this is actually a study that done at Hespler Farms. We also want to be able to, I mean, this is one study. I mean, there's no way we can study every site. So, and also there's no way to do this in multiple years as well, because it's too costly. So what we normally want to do is trying to model this field in a computer. So we create a computer model of the field based on the data we collect over 2 to 3 years. So in this case, you can see we modeled a particular field. This is 2019, 2020. This is the Pese site. You can see the dotted lines are the simulated water table depth, and the at least in the dashed lines here in the bottom graph, and then the solid lines are the actual measured water table depth. And you can see pretty much matches what is being observed. So once we model the field and calibrate and validate the model, then we can run simulations using rainfall patterns from different years. So if I go to a different year, now this is again a complex graph showing at different years the impact of using different drain spacing. So we tested 8 meters, 15 meters, 30, 50, 70 and 90 meters, and we looked at the relative yield. And for different years, you can see as you increase the drain spacing, the relative yield goes down. Some years it's worse, some years it's not that bad. It all depends on the rainfall for that particular year. If it's a dry year, drain spacing is not going to have much of an effect. But if it's a wet year, you're going to have an effect, and the drain spacing will matter. So you can actually model this for every field and then determine what would be the optimum drain spacing. So this is one area that we try to optimize the design. Here's another study where we actually use this data to predict the cost implications. Obviously, when you bring the spacing closer together, it costs more money. So we looked at the yield impact of increase in the spacing, and then also looked at the profit related to closer space drains. And then we kind of optimized the design to about 10 in this case, 10 meters. So this kind of a study will tell you, using long-term data, what would be the profitability of putting drainage system and what would be the spacing we need to use for a particular field. So this actually is based on field data and then trying to develop a model and then using the model to predict what might happen under different rainfall patterns in different years. Now we also looked at, in another study, we looked at the workable days. In this case, we were looking at the soil moisture status in the top 2 feet of the soil. So as long as the top 2 feet of the soil, the water content is below the lower plastic limit for that particular soil, we can get on the field without causing compaction. So then we do a count of how many days we can get on. We also looked at the non-workable days and the total number of non-workable days. And based on this study, we found that around 12 meters is the spacing for this particular soil. So this kind of analysis helps us determine or at least optimize the drainage spacing. So based on all of these studies, what we found out was we still have to get the drain spacing closer than what we are normally doing here. So I would say around 8 to 10 meters is probably the best way to go. And if you're going to put them so close, then there are other benefits as well. So that's what I'm going to talk about in the next few slides. So when you have the trial drain spacing less than 12 meters, we can also use it for sub-irrigation. And I will talk about that later on in the when I explain what sub-irrigation is all about. Now, in addition to all of these, we also need to know what depth we need to install the drain, because the depth of the deeper you install, the wider you can go. But it affects the sub-irrigation potential. So because we are installing closer together, we can install them shallower, which is much better for sub-irrigation. So there is a trade-off there. So we need to look at that as well. Now here's another study that was done, this was in Hespeler farms. Basically, you can see some years there's a yield reduction. If it's a deficit year, having any like 1989, the yield would have been very, very low. Whereas if you look at the year 2006, somewhere here, you can see that as you increase the drain spacing, the yield goes up, mainly because this was a dry year and narrow spacing was actually draining the water. And this is actually modeled after a free drainage. That means we are not controlling the amount of water outflow. In many years, like in year like 1992, the rainfall pattern, it was adequate, so no amount of the spacing didn't matter much. Whereas if you look at 1991, there was slight excess, but up to a certain level, there was not much effect. There are no effects in these years where the rainfall was okay. But if it's a wet year, then of course the spacing matters. If it's a dry year, the spacing will affect the opposite way. So the main idea here is to not overdrain the field. So if you're not going to overdrain the field, there is this practice called control drainage, where you're trying to limit the outflow from the free drainage. So there are techniques that are available to limit the outflow, and this is where the control drainage comes into play. So with control drainage, what we do is we have at the end of the tile at the outlet, there's a gate like shown here. We can raise and lower this gate to control the level of the water inside the field. But as you can see here, if the field is sloping, you might cause an uneven depth of water within the entire field. As a result, you might defeat the purpose of having a control structure. So in this case, you may want to have an inline control structure along the length so that water surface will be dropping at foot intervals as you go down slope. Now, before the control drainage came into play, most of the field drains are installed downslope because obviously for transmitting the water, the faster the water flow, the narrower or the smaller the drain you can use. So you can move the water faster if the field drains are downslope. That was generally the practice for decades. But with control drainage, it'll be a design not conducive for control drainage. Because in control drainage, you want the field drains to be on the contour so that there'll be even spreading of the water, and the downslope will be the collector drain or the submain. So let me show you how that works. So here you have the field drains going parallel to the field, like almost on the contours, with the submain going downslope with control structures called water gates installed, so they step the water at 1 foot intervals. So by blocking the water at the outlet right here, water will back up and it'll go one step up and it'll back up and one step up and it'll back up like that. So this way you have the entire field, the water level can be controlled with one outlet point. But this requires careful design. So this is the part that I wanted to convey as the main component of this study, or at least this presentation, is that the orientation of the tiles that are installed are very critical to make this work properly and to gain the benefits. Now, if you're going to control the flow like this, you can also apply water through the tile. So let's look at that. Now, here's one other study that was done where it shows if the main tile drain was like this, and if there is no water gate, without the water gate, the water level would have been like this. But because they put the water gate, the water level is like this, the ground surface is like that. It's almost kind of same distance everywhere. So you can see right away the benefits of having the water gates, so you can follow the contour or the surface of the land. So it is very important. This is a particular study that was done, reported by FOSI. I think this is North Carolina State University. So this is another study that was done, recently reported. I would say 10 years ago, actually. Here is a pictorial representation of free drainage where we have the control structure, but the control structure level is below the tile drain. So it's freely draining. Water level is freely draining. This is what you will do in the springtime. But you can raise the level of the gate and push the water back and limit the amount of water going out of the tile through control drainage. But if you're going to do a control drainage, you can also apply water this way on the upstream side of the control structure, so you can push the water back through the tile. Now, this particular model works if the field is relatively flat and you don't have much of a slope. But if it's a sloping field, your water needs to be applied from the other end. I would say it will be much better to apply from this end, because it will be impossible to push the water through this way if you have inline control structures. So that is a limitation of the design, and that something needs to be considered looking at the overall slope of the field. So these are the three different modes in which the control structures can be operated. One in the free drainage mode in the springtime, and the other one is a control drainage mode when you anticipate there is not going to be any rainfall and you don't need to drain the field completely. And if you want to sub-irrigate, you can apply water back through the tile. Now, what are the problems? The upward flux of the water to meet the plant water uptake works against gravity. And the upward flux is also affected by soil water content. If the soil is dry, the upward flux is going to be limited. The wetter the soil, you're going to have greater upward flux. So the soil moisture in the upper layers, at least in the root zone, will control the upward flux. And the layered soil will also affect the upward flux. If you have any kind of sand lens, the upward flux will be limited. So this is something that should be kept in mind before we design the system. So soil sampling in the field to determine the horizon and the variation in the texture of the soil needs to be considered. And some of the things we can do is to input this information into a computer model and then run simulations with 30-year weather data and then predict what might happen. So before putting a whole lot of money investing into this system, maybe it's better to do a little study and evaluate the field for the appropriateness, or at least for the situation at hand. Now here is a model, a subrogation through the tile. This was actually done on the site at Pesay. You can see the tile is located with a, you can see a black round here, and on the right hand side, that's the mid spacing. So this pattern is repeated one after the other. So tile to the mid spacing. So if I start the simulation, this particular field was completely dry, and we needed to quickly apply some water so we can germinate the plant. So what we did was we applied the water through the tile. And let me see if they can run the simulation here. As you can see, it's running. You can see water is spreading. And then the surface, the red the color is, the drier it is. The blue, the more blue the color is, the wetter it is. So we are applying water through the tile, and it is spreading slowly towards going below as well as above. But if I increase, then you begin to see that there is some wetting on the surface. That's because it rained in that particular field. So when it rained, it actually added moisture on the surface, and then over time, let me run the simulation to show you what's happening. So over time, the simulation was done over 30 days. You can see it is making a connection. So once the rainfall occurred, they stopped the flow, and then they applied water again, and you can see that it's continuously spreading all the way up. So as long as the soil remains wet, you can actually supply the water from the tile all the way to the middle in between space of the drain tile. So it is effectively you can irrigate using the tile. But if the rain didn't happen, then there will be a hydraulic connection problem, and in that case you may have to use pulse application. And again, that's what we are trying to optimize now as to how to operate the sub-irrigation if there's no rainfall at all. That'll be a tricky situation. Again, this is a model of the field in Pesay site, which is completely clay. In fact, it works better on clay soils than in sandy loam soils. So some of the advantages of sub-irrigation through tiles would be you don't have to have additional irrigation equipment, and of course no labor, and also water is directly applied to the roots, therefore it can be automated, and leaf canopy is not wetted, which has an advantage because now you can prevent any kind of fungal disease or anything like that. So there is that savings there. There's also a higher application efficiency. Again, if you continuously apply, water will actually go down below the tile due to gravity. So that's something that you need to control how you're applying. There's a protocol to follow when you're applying this one. In all of this to work, the installation depth is very important, because the drainage installation, if it is too deep, it may not work as effectively as it is shallower. So let's look at the impact of the depth of installation. Now here's another simulation that was done at the Hespeler farms, and in this case we actually looked at the water table depth kept at 1.3, 1.1, 1 and 0.9 meters depth below the ground surface. So I'm going to show you a series of simulations over from 55 days to 104 days after planting, in a potato field. So this is another study that we did long time ago, and the data was collected a long time ago, but the simulation was done a couple of years ago. So let me show you what happens. We start with the deeper depth. So when the drain is located at 4.3 feet, rainfall will cause the water to infiltrate down. We'll wait for the simulation to continue. So as it is coming down, you can see it's going down, also going down below the 1.3. So it's going below the 1.3 level. There's very little water being pulled up the other way. The arrow is pointing down. So this is for 1.3 meter depth. Now if you go to the next depth, 1.1 meters is going down, for the rainfall is going down, and as it gets wet, it keeps going down, and the plants are evapotranspiring, but there's no chance that it's being pulled up the other way. It's pulled up, but you can see on the surface water is being taken up, but very little is beginning to move up at 1.1 meters. Let's go to the next level, which is 1 meter below the ground surface. In this case, water is going down to the water table, which is located 1 meter below the ground surface. So now when there's no rainfall, evapotranspiration is pulling the water up, and you can see there's a connection from below. So it's beginning to pull water up from 1 meter below. So it is effective at around 1 meter depth. So it's easier to pull the water up. When you go to 0.9 meters, which is about 3 feet, you can see that it's going down. And then when there's no rainfall, when the evapotranspiration takes place, it's beginning to connect easily and pull the water up very effectively. So you can see that it's supplying much better. So in Manitoba, usually we install the tiles around 0.9 to 1.1 meters. That's what we have done in our fields. So it kind of looks like it's very critical, the depth of installation. If you're going to use it for sub-irrigation, also for controlled drainage too. So the closer it is to the surface, it's better. But that means we also had to go closely spaced drains. So that is the important takeaway from this particular simulation. So in summary, the soil profile information is very critical. If you have any kind of sand lenses or different texture soil in the horizon, then it's going to affect how the controlled drainage or sub-irrigation is going to function. So that is important, because then when you're doing planning for the system, it might be better to take soil samples in the profile and then try to model this one and see how well it works using multi-year rainfall data, and then making sure that you optimize the design. And also maintaining the hydraulic connection is important. So what it means is the soil must be not, you shouldn't allow the soil to dry too much, because the drier the soil, the lower the upward flux. Because the hydraulic conductivity or the ability of the soil to transmit the water will be affected by the soil moisture content. So you don't wait till the soil dries out before you start to irrigate. In this case, you start to irrigate closer to that as you're beginning to lose. And if you forecast that there's going to be a dry spell coming up, then you start to sub-irrigate early on. Now, we also did some study. This is a previous study in Hespeler farms. We looked at nitrate export. In the FDIR stands for free drainage with overhead irrigation. CDSI stands for controlled drainage with sub-irrigation. So, but this study was done back in 2010, 2011. You can see that the free drainage actually exported a lot of nitrates But most of this happened during the springtime. Similarly, we also looked at the phosphorus export. It also happened in the springtime. The control drainage or the control structures actually limited the outflow of the water, thereby limiting the amount of phosphorus export. So what it means is, in the springtime, if you're going to drain the water, it'll have lots of nutrients. If there's a way to hold the water back, some other off farm storage, it'll be ideal to do that, so you can also use it back to irrigate later on in the season. So that is something to consider. I think other jurisdictions like in North Dakota and other places, people are considering holding the water back in off-farm reservoirs. At least in Hespeler farms, they're not doing from the farm, but they're actually holding the spring snowmelt. But there's no way, there's a way to, you can pump the water back into the same reservoir, but they have not done that yet. But it is possible to do that. So it does help to hold the water back in the springtime, because most of the nutrient export happened during the springtime from the tile drainage. Now, based on all of this research, we wanted to develop a demonstration facility on campus here. What you see on the top left, right here, is the point at the University of Manitoba campus. Through the ESCAP funds, we were able to install tile drains the conventional way, which is downslope here. The slope is this way, and this is the cross slope on the contours here. So 2-acre plots. So we have installed this one, and the collector drains are going into a sump pit individually, and we are using a solar panel operated pump to pump the water that is coming out of these 2-acre plots into these storage tanks. And we are going to use this water. This is the first season that we are trying to collect the water, because it's installed last end of around the fall, around August, September. We installed this, and then we are going to collect the water and then pump it back through the tile to irrigate. So this is the plan, and this will serve as a demonstration plot for anybody to come and see how this works. And we haven't planted yet. Coming season is the first time we're going to plant. The idea will be to compare the differences in yield coming from location here versus location here versus location here and location here, depending on how you're going to operate the control structure. Because the land is sloping this way, the cross slope is minimal. This is a minimal slope along east-west, or in this case, yeah, going east-west, whereas there's more slope going north-south. So we will see the impact of this one in the coming seasons. There'll be a lot more studies done in this particular site. So anytime anybody wants to come and take a look at this particular location, you're most welcome to connect with us and come and see the place. We might have some open houses towards the end of next season. So in summary, I just wanted to say the control drainage management can conserve water and nutrients within the field, and it is possible to sub-irrigate through the tiles very efficiently. So that way you can also reduce the water usage. So if you want to consider using control drainage and sub-irrigation, it is very important to put the tile drains on the contour, almost on the contour, with the sub-mains running downslope. That is the most important takeaway from this discussion we are having today. And you can use inline control structures that are installed on the sub-main. So this way you reduce the cost. You don't want to put inline control structures on the field drains because there will be too many. So this is the best design to go with the inline control structures on the sub-mains, and ideally you want to evaluate the field before you embark on a drainage installation. And then, of course, if you're going to sub-irrigate, it's going to be done through the high end of the sub-main, because if you have inline control structures, you wouldn't be able to push the water through the other way. You can only push the water one way from the far end of the field. So those are some important considerations to keep in mind when you are planning the system. So that's all I have, and I will be more than happy to answer questions.
Hey, thank you, Dr. Ranjan. If you have any question, you can use the Q&A section, or you can use the chat box to type in your question. If you prefer to speak, just raise your hand. I'll unmute your mic so that you can speak if you prefer to speak instead of typing. There's a question. Have you done any work with doing till drainage in heavy clay soil on fairly flat land, flat field?
Yeah, our site actually in Pesay is relatively flat and it's heavy clay. So if you have a chance to visit the Pesay site coming season, please do, and then we can arrange to meet there and explain to you what's going on. Some of the results I presented here are from Pesay site.
Okay.
In fact, the sub-irrigation works very well in the clay soils.
We've done so as well. Okay. Another question. What is the average cost for the I think you want to say control
drainage system, yeah. So I looked at the price today. I think those control structures cost about, each control structure costs about like $600 US. And they only are put at the outlet. I don't know the price of I think the inline control structures are around $500. But we didn't put any inline control structures at the point site because it's very flat. The inline control structures are necessary only if there's a foot drop in elevation, if the land is sloping. And very few places here in Manitoba, at least that I know of, are that sloping. So the need for inline control structures may not be there, but you still need some slope for the water to flow. So the overall cost of things, $500-600 on a quarter section is a tiny fraction of the cost of drainage, because it costs about, I think it's around $1,500 to $1,800 per acre to install tile drainage, right? So when you consider all of that cost, control structure only comes at the end of the tile outlet, right? So it's pretty small.
Okay. Thank you. Another question. In heavy clay, should there be a specific sock or cover on the tile?
Yes. I think most, okay, let me explain that. I think that's very important, very good question. Let me draw and explain. The corrugated tiles are like this. The corrugated tiles are like this, and the slots openings are cut like this at the inner end of the tile. So having a sock around the tile like this keeps the soil away from this area. So this area, now the water will enter here and is free to move around the annular space. So it reduces the resistance for water to enter the tile. So having the soil not only functions to keep the soil particles from entering the tile, but also it improves the resistance for water to enter the tile. Right? So it is very important that you always get the tile with a sock. Okay, and I think that is how they are sold anyway. So you can, if you don't have the sock, then what will happen is soil particles will collapse into this area. Soil particles will collapse into the gaps here, and the resistance to flow through the holes will be much more. Right? So in addition, so it wouldn't drain as well as if you had the socks. So socks play not only to keep the soil particles out, they actually reduce the entry losses. You know, the hydraulic losses happen that happens at the tile itself.
Okay. So is there a specific one, or generally any socks would work or cover would work?
Yeah. Like they have a it's like a plastic material, woven plastic material that is stitched onto the surface of the tile. That's how it is supplied. All tiles are supplied with the sock, and sock, the main purpose of the sock is not only to prevent the soil's particles from entering the drain, but more than that, reducing the entry losses.
Okay. So, can you comment on drip irrigation, what equipment it needs, and how much water it can save?
Okay, drip irrigation is on the surface, and I would say at 10 cents a foot, it'll cost $250,000 to install drip irrigation for a quarter section. From a cost point of view, is way more costly to install drip irrigation on a farm field compared to any other, like a center pivot system or any other system. But for a small home garden, I think drip irrigation is fine. You can buy parts off the shelf. You can order them on Amazon. There's a supplier here in town you can buy, and you can install. Again, you have to control how much water you are putting into the tile, into the drip system. And one of the things we had to be mindful in Minipec at least is the water, the deposits, because the emitters can get clogged because of mineral deposits. So it is important to balance the water before you put it into the uh, drip system. Otherwise, you're going to have clogged emitters, and you're going to have to destroy the emitters pretty soon.
Okay, okay. I think there's another question. Or before then, let me just ask the question as a follow up to the socks. Um, w- you would would you sock it in heavy clay? I don't understand. Maybe they might want to provide
What is the
clarity.
name? I can read the question here. Is it the
Melin,
whose question is this?
melin.
Should there be a specific sock cover? There's only one kind they sell with the sock, right? It's a woven fabric they sell. It's already made by the tile manufacturers. They do this.
Okay. In early 2010, there was a fast expansion of tile in Manitoba. What's the
Yeah.
current status today?
Okay. I must tell you, when I first saw the tile installed, that was 1992. I drove to McGregor, Manitoba, just to see the tile being installed because I want to take a footage of the tile installation to show in my class. That was, I think, back in 1992, 93 sometime. And the installer was from Ontario. And when I talked to him, he said he's booked solid for 3 years. There was no installers in Manitoba at the time. Then he sold his machine to Precision Land Solutions, I believe, and they were the operators for a couple of years. And then in 2010, there were maybe 2 or 3 operators. Now there are more than about 10 or 12 installers, and there are 2 manufacturing plants for tiles in Manitoba now. One in Carman and the other one is in Winkler. So we are manufacturing our own tile drains in Manitoba now. We used to get them from the US, but now we have our own plants here.
Okay. So, please contract sub irrigation design for a fine versus coarse texture soil, such as with respect to spacing.
I didn't get the question.
Please contract, like I think he's trying to ask that you should compare between sub irrigation for both fine and coarse texture in terms of the
Okay,
spacing.
okay. Sub-irrigation in coarse textured soils is going to be tricky because it wouldn't spread as as well as in a fine textured soil. And generally, for coarse textured soils, it'll be well drained anyway. So you may not have that much of a benefit by putting a tile drainage. You're going to put tile drainage in fine textured soils anyways, right? So unless you have very high water tables and you're trying to control that, it'll be less effective in coarse textured soils.
Okay, okay. Another question: in heavy clay, how much infiltration efficiency could a farmer expect when reusing captured thawed rainwater?
Okay. What is the question? In heavy clays, how much infiltration efficiency could the farmer expect when you using captured tile rainwater? I would say, like, if you apply the water at the right time, you would be able to, the capillary movement itself will be able to supply the water, as I showed you in the simulation. But you shouldn't be waiting till the soil dries out too much, because the wetter the soil, the easier for the water to move from one location to the other through the soil, right? So it is important when you apply the water. You don't want to wait till the soil dries out. Then it becomes impossible to apply the water. So that's why I think it's important to have soil moisture sensors installed. Even otherwise, you should have soil moisture sensors installed to manage the water properly anyways. I think that is something that's a given. But most people don't do that. But I think knowing what's happening beneath the ground surface is very important to manage the water properly, right?
Okay. Please comment on the merits of active sub-irrigation versus passive holding back drainage water system in terms of features, design, and cost.
Okay. Controlled drainage structures are necessary to hold the water back. I don't think you need to drain the field completely to get the benefit of this, because we don't have to freely drain all the water out of the field. So if you can partially drain the water, controlled structures can help you hold the water back in the field if you anticipate a dry spell in the coming weeks or so, right? So that is the advantage. But if you're going to hold the water back, and if the field is relatively flat, then you can apply the water back through the tiles. That's what I call sub-irrigation, right? But then, of course, you need to have a storage structure to hold the water too. But I think when you consider the amount of nutrients that are taken out during the springtime, that is going with the drainage water, holding that water might be useful too, right, in the long run. In fact, that is what is being promoted, at least in South Dakota. People are being asked to hold some of the water back again as a flood control measure. But I think it's more than that. I think holding the water back can be very, very helpful.
Okay. Any other question? Let's see.
So I had actually displayed my, let me see if I can share the screen again. Just displayed my email. So if you have any questions, you feel free to send an email request. And we are actually continuing our study at the PESE site. I'll be more than happy to show you what's going on there. We do have field days organized at PESE site. I don't know when, but usually it happens in July. So feel free to come by and see what's going on. And if anybody is planning to install drainage tiles, I think before you put down millions in investment, it might be worthwhile to put a piezometer or at least a water level sensor in your field and monitor the level of the water at least for one season. You have a better idea how to design the system for your field. Unfortunately, nobody does that, but I would say it's a worth investment because it'll cost about maybe I would say less than $2,000 to put one in, but you will save yourself lots of money in the design and making it more effective for your field.
Okay. I think one last question. What are outstanding research gaps, particularly in this region, with a unique combination of climates, landscape, and soil condition?
Research gaps. Right now, we are trying to refine how the sub-irrigation should be operated, because I think there's a benefit, because we think under Manitoba conditions, with the rainfall patterns being highly intensive rainfall followed by droughts, we need faster drainage. Therefore, we need to go narrower spacing. But my point is, if you're going to go narrower spacing, might as well use it for subrogation. So we are trying to develop a protocol how you should manage subrogation through tiles and control drainage. That's what we are trying to address in the coming years. So that's very important. And also, as with any water application to soil, monitoring the salinization of the soil is also important. So that's another area that we are working on, doing EM surveys of the field to assess what's going on in the long run.
Okay. Thank you so much, Dr. Ranjan. Thank you for sharing your insightful research with us. We really appreciate your time and presentation. Just to let you all know, this webinar would be available online in our website, which is the UM-RAE website. You can see previous webinars. We also have fact sheets and podcasts. So we'll have it in this section under the Make websites in Faculty of Agriculture. So if you still want to go back and maybe there's something that you didn't get here clearly, you want to get more information, you can still go online and watch the video of the webinar again. With that, we've come to the end of today's webinar. I want to thank you all for attending, and please stay tuned. Watch out for emails. Check our website to see what's the next webinar, which topic we'll be covering in our next series. Thank you all for attending, and do have a wonderful rest of your day.
Thank you.
Thank you.